Hey everyone, and welcome to another deep dive. Today we're going to unpack something that's been blowing my mind lately.
Yeah.
The whole world of exoplanets. I
Yeah.
mean, think about it.
Yeah.
We went from not even knowing for sure if there were planets around other stars to now having thousands of confirmed exoplanets
Yeah.
and even more
It's
candidates.
amazing.
It's amazing. It's crazy. And today we're going to dive into not just what we found, but how this whole scientific journey even happened.
Right. And it's really a story that goes back way further than you might think.
Yeah, I was surprised too. So we've got this stack of research and articles. And one of the first things that jumped out at me was how even ancient Greek philosophers were already kind of thinking about this stuff.
Oh, yeah, for sure. I mean, they were already contemplating other worlds, other planets out there. It just
Mm,
shows you that, the human fascination with what's beyond our little corner of the universe.
just been there forever.
It's always been there.
But of course, it took a long time,
Oh, yeah.
like centuries, to actually start finding these exoplanets because it's hard. I mean, can you imagine trying to find a planet orbiting another star? It's like
Well, the distances are so vast.
they're enormous.
Yeah.
And it's not like planets shine like stars do. They don't have their own light. They're just reflecting the light from their star. It's tiny.
It's incredibly faint.
Yeah. So one of the things I kept seeing in these articles was this term, expensive star systems. And I got to admit that threw me off at first. What does expensive even mean when we're talking about stars?
Yeah, it's a bit of a weird term, isn't it? I mean, it doesn't mean that someone's charging us money to look at a star, right? It's more about how difficult it is to study certain star systems. Some are way harder than
Oh,
others.
it's so expensive in terms of the effort and the technology you need.
Yeah, exactly. And there's a bunch of reasons why some stars are so expensive to study. One of the biggest factors is just distance. I mean, the farther away a star is, the fainter its light. So it's already harder to see. And then
Yeah.
you're trying to detect these teeny tiny wobbles or dips in the light that are caused by a planet orbiting it.
Right. It's like trying to hear a whisper from across a football field.
Pretty much. And then on top of that, you've got stars that are just ridiculously bright.
Oh, yeah. Some of those are blinding.
Oh, they're super luminous. And that makes it even harder to see any planets around them. It's like trying to spot a firefly next to a spotlight.
Ah, okay. So it's like the star's own brightness drowns out any trace of the planet.
Exactly. And then you've
Yeah.
also got things like where the star is located in the galaxy.
Ah, right. Location, location, location.
For example, stars that are in really crowded regions or behind thick clouds of cosmic dust, those are super tough to observe.
Yeah, like trying to see anything in a blizzard.
Exactly. And then you also have stars that are just weird. I mean, some stars rotate super fast, or they have these strange emissions that make it really hard to study anything around them.
So you've got distance, brightness, weird stars. It sounds like a recipe for astronomers to just pull their hair out.
Yeah, I mean, you got to give them credit. They were really persistent, even with all these challenges.
Yeah, I mean, they didn't give up, and eventually it paid off.
Right.
And that's where this whole story of 51 Pegasi d comes in, right?
Oh, yeah. 51 Pegasi b is a huge deal in the history of exoplanets.
It was the first one, right?
Yeah.
Like the first confirmed exoplanet orbiting a sun-like star.
Yep. And it was discovered back in 1995.
October 6, 1995.
Yeah.
Like I have it circled here in this article.
Yeah, a date that changed everything.
But what's really interesting is that 51 Pegasi b, it wasn't just the fact that it was the first one discovered. It was what kind of planet it was that really threw everyone for a loop, right?
Absolutely.
So what was so weird about 51 Pegasi b, what made it so different from what everyone was expecting?
Well, for starters, it's a gas giant, like Jupiter.
Okay, big and gassy, we got that.
Right. But here's the thing. It's orbiting incredibly close to its star. Like way closer than anyone thought a gas giant could be.
Wait, hold on. Didn't we learn that gas giants form way out in the solar system where it's cold? I mean, that's how Jupiter formed, right?
Yeah, that's what we thought, yeah. But 51 Pegasi b is hugging its star. Like it's orbiting at just 0.05 AU. For comparison, Jupiter is out at 5.2 AU.
Wow, so 51 Pegasi b is basically right next to its star.
Yeah, it's practically touching it.
Okay, that doesn't make any sense. How does a gas giant even get that close to a star?
That was the million-dollar question, and it's what made 51 Pegasi b so groundbreaking. It just completely challenged our understanding of how planetary systems form, and it led to this whole new idea of
Yeah.
planetary migration.
Planetary migration. So you're saying that planets can move around after they're formed?
Not exactly move around, but yeah, the idea is that gas giants can shift their orbits over time. They can actually migrate inwards towards their star.
Hold on, I'm still wrapping my head around this.
Okay.
So a gas giant forms out in the cold reaches of a solar system, and then it just decides to take a stroll closer to the sun. Why? What causes that?
Well, there are a few possibilities. One is gravitational interactions with other planets in the system. Imagine like a cosmic game of billiards where the planets are nudging each other around, and sometimes that can send a gas giant spiraling inwards.
Oh, wow. So it's like a chaotic dance.
It can be. Another possibility is interactions with the protoplanetary disk, the cloud of gas and dust that surrounds a young star.
Oh, right. So it's not just where a planet forms that determines its final location.
Right.
It's these gravitational interactions that can cause it to migrate over millions of years.
Exactly. And the discovery of 51 Pegasi b and a bunch of other hot Jupiters like it, well,
Yeah.
it really suggests that planetary migration might be more common than we initially thought.
So our nice, neat solar system, with the rocky planets enclosed and the gas giants far out, maybe that's not the norm after all.
It really makes you wonder how unique or common our solar system really is.
Yeah, and it just shows how diverse planetary systems can be.
Out there in the universe.
Yeah, and 51 Pegasi b, it wasn't just a one-off discovery.
No.
It kicked off this whole new era of exoplanet hunting.
It did. It was like everyone suddenly realized, hey, there are planets out there, and we can find them.
Yeah, and the technology just exploded after that, right?
Yeah.
Like new telescopes, new techniques.
Exactly. They started refining existing methods like the radial velocity method, which looks for those wobbles in a star's motion.
Right, right.
And then they developed new techniques like the transit method, which is all about looking for those tiny dips in starlight when a planet passes in front.
It's like we went from a magnifying glass to a high-powered telescope.
And with those new tools, they started finding exoplanets all over the place.
Yeah, and the numbers are just incredible. I mean, thousands of confirmed exoplanets and probably billions more out there
Yeah.
just waiting to be discovered. It's mind-blowing.
Absolutely. And it just keeps getting more exciting as new telescopes come online, like Kepler and TESS, and now James Webb Space Telescope. It's a whole other level.
Oh yeah, the James Webb. That's the one that's going to blow everything wide open.
Sure.
But before we get into that, let's take a closer look at some of these new technologies.
Right.
The ones that are really pushing the boundaries of what we can see and learn about these distant worlds. I mean, we've got to talk about direct imaging, right? This idea of actually seeing exoplanets. I mean, come on, how cool is that?
Oh, it's incredible. Direct imaging is a game changer. It's like going from those blurry black and white photos to high definition, full color images.
I'm ready for the color. So tell me, how does it even work? How do you see a planet that's like trillions of miles away and drowned out by the light of its star?
It's all about these incredible instruments called coronagraphs and adaptive optics.
Yeah, coronagraphs and adaptive optics, they're really the secret sauce behind direct imaging.
Okay, so break it down for me. How do these things help us actually see exoplanets?
All right, so coronagraphs. Imagine you're trying to look at something small and dim right next to something super bright, like a firefly next to a spotlight. What do? Try to block the spotlight, right? Use your hand or something.
That's exactly what a coronagraph does. It blocks the light from the star so we can actually see the faint light from the planet.
Oh, that's so clever. So it's like creating an artificial eclipse inside the telescope.
Exactly. And then you have adaptive optics, which tackle a different problem. Earth's atmosphere.
Yeah.
Our atmosphere is constantly moving and swirling. It's like looking through a pool of water that's constantly rippling.
Right, it distorts everything.
It makes everything blurry, especially those faint, distant objects. So adaptive optics, they're basically like putting glasses on the telescope.
Glasses for a telescope. That's awesome.
They constantly adjust to counteract the blurring effects of the atmosphere. It's amazing technology.
So you've got the coronagraph blocking the starlight and the adaptive optics sharpening the image. It's like a 1-2 punch.
It's a powerful combination.
Yeah. So with direct imaging, what kind of planets can we actually see?
It works best for large planets
Okay.
that are relatively far from their star. Think big, bright, and far out.
So like Jupiter, if it were orbiting another star.
Yeah, exactly. The bigger and brighter a planet is, and the farther it is from its star's glare, the easier it is to spot directly.
So the smaller rocky planets, the ones that are more Earth-like, are those still out of reach?
For the most part, yeah. Direct imaging is still a bit limited when it comes to those smaller, dimmer planets that are huddled close to their stars.
Oh man, I was hoping for a glimpse of another Earth.
Don't worry, the technology is constantly improving. Who knows, maybe one day we'll be able to directly image those Earth-like planets too.
I'll keep my fingers crossed. But it's not just about seeing these planets, it's about understanding them.
Of course, that's the whole point.
So what about those planets that are just too faint or too far away for direct imaging? How do we study those?
Well, there are other techniques, like gravitational microlensing. Now, that one is really wild.
Gravitational microlensing. I remember seeing that in one of the articles. It sounded like something straight out of Star Trek.
Yeah, it's kind of mind-bending. It uses the gravity of a star to bend and amplify the light from a more distant object, like another star or even a planet. It's like a cosmic magnifying glass.
Wait, hold on. Gravity can bend light, like actually bend the path of light.
Yep, that's Einstein's theory of general relativity for you. Massive objects warp the fabric of space-time, and that warping can act like a lens, bending the light that passes nearby.
Whoa. Okay, I think I need a minute to process that.
Yeah.
So if a star passes in front of another star, its gravity can magnify the light from the background star.
Precisely. And if the foreground star has a planet orbiting it, that planet's gravity can cause a little blip in the magnified light. It's a tiny signal, but it's enough to tell us there's a planet there.
That is so cool. It's like using the entire universe as a telescope.
Pretty much.
But I'm guessing this kind of alignment, where one star passes directly in front of another, that can't be very common, right?
It's pretty rare. Gravitational microlensing events are fleeting and unpredictable, but they allow us to see planets that would be completely invisible to us otherwise. It's like catching a glimpse of a firefly in a distant forest during a lightning storm.
Wow, that's a perfect analogy. And these rare events, they can reveal planets that are really far away, right?
Yes, gravitational microlensing is great for finding planets that are way out there, especially those that are orbiting stars in the galactic bulge, the center of our galaxy.
So it's like we have these different tools for different jobs.
Yeah.
Direct imaging for the big, bright planets, gravitational microlensing for the distant ones.
It's like building a cosmic toolkit, each tool allowing us to see different parts of the universe.
Exactly. But it's not enough to just know a planet is there, right?
Right.
We want to know what it's like. What's its atmosphere made of? Does it have clouds? Could it support life?
Of course. And that's where atmospheric characterization comes in.
Ah, yes, atmospheric characterization.
Mhm.
That was another term that kept popping up in my reading. It has something to do with analyzing the light that passes through a planet's atmosphere.
Exactly.
Yeah.
It's like taking a fingerprint of a planet's air. When a planet passes in front of its star, some of the starlight filters through its atmosphere, and that atmosphere absorbs certain wavelengths of light, leaving behind a unique pattern.
A fingerprint of light. That's amazing.
It is. By analyzing that fingerprint, we can figure out what the planet's atmosphere is made of. We can look for things like water vapor, methane, oxygen, ozone.
So it's like we can actually sniff the air of a planet millions of miles away.
In a way, yes. And this information can tell us a lot about the planet's temperature, its climate, and even its potential for hosting life.
Okay, now we're talking. This is where it gets really exciting.
It is, isn't it?
So we can look for signs of water vapor, methane, oxygen, all the ingredients that we think are necessary for life as we know it. But what if we find a planet that has all the right stuff, but no signs of any advanced civilizations? What if life beyond Earth is just microbial?
Well, first of all, finding even microbial life on another planet would be a monumental discovery.
Oh, yeah, for sure.
It would mean that we're not alone in the universe, that life isn't just a fluke that happened here on Earth.
Right. It would mean that life could be a common occurrence throughout the cosmos.
Exactly. It would be a paradigm shift in our understanding of our place in the universe. It would be huge. Even finding tiny microbes on another planet would change everything.
You would rewrite the textbooks for sure.
Yeah, and think about it. It would mean that life isn't this fragile, unique thing that only happened on Earth.
Right. It could be happening all over the universe, maybe even in our own cosmic backyard.
Exactly. And that brings us to the big question. Are we alone?
The million-dollar question.
Uh-huh.
And after this deep dive, I gotta say, I'm feeling a lot more optimistic about the answer.
Me too. I mean, look at all the evidence we've uncovered, the sheer number and diversity of exoplanets out there.
It's mind-boggling. We've got hot Jupiters, super-Earths, mini-Neptunes, planets orbiting pulsars even. It's like the universe is a cosmic zoo of planets.
And with all that variety out there, it just seems statistically improbable that we're the only ones, right?
Right. But finding proof, well, that's the challenge.
It is. It's like searching for a needle in a cosmic haystack. But we're getting better at it all the time.
Yeah, with tools like atmospheric characterization, we're not just looking for planets anymore. We're looking for signs of life.
Exactly. We're analyzing the air of these distant worlds, looking for those telltale chemical signatures that could indicate the presence of life as we know it.
So things like water vapor, methane, oxygen.
Those are the big ones. And finding them together, that would be a really strong indication that something interesting is happening on that planet.
Right. It's like a cosmic recipe for life.
Kind of. But even if we find a planet with all the right ingredients, It doesn't necessarily mean we'll find little green aliens waving at us.
Yeah, I'm not expecting any interstellar welcome parties anytime soon.
But even finding microbial life, even the simplest single-celled organisms, that would be a revolutionary discovery.
Oh, absolutely. It would change everything we thought we knew about life, the universe, everything.
It would force us to rethink our place in the cosmos. It would be humbling
And exciting.
and exciting, absolutely. It would open up a whole new world of possibilities.
And who knows, maybe someday, down the road, we'll find evidence of something even more complex, more intelligent.
It's definitely possible. I mean, the universe is a vast and mysterious place. We're just scratching the surface of what's out there.
Well, this deep dive has been one heck of a scratch. It's amazing to think how far we've come in just a few decades.
It really is. From not even knowing if exoplanets existed to actually searching for signs of life on them. It's a testament to human ingenuity and our insatiable curiosity.
Absolutely. And it makes me so excited for the future of space exploration, for all the discoveries that are yet to come.
Me too. Who knows what we'll find next?
That's the beauty of it, isn't it?
Yeah.
The universe is full of surprises. Well, on that note, I think we've reached the end of our deep dive. Big thanks to you for guiding us through this incredible journey through the world of exoplanets.
It's been my pleasure. And thanks to everyone out there for listening in. Keep looking up.
And keep exploring.